Hello students, in today's lecture we are going to discuss about moment of inertia of a ring. So, in case of a ring we can determine the moment of inertia about an axis passing through the center of the ring, about an axis passing through the tangent, about an axis passing through any diameter. So, first of all we can determine the moment of inertia of a ring. So, for that purpose we have to consider a ring. Suppose this is the ring, it is the thin, uniform and circular ring. So, this is the axis of rotation about which the ring can perform the rotational motion. Suppose capital M, it is the mass of a ring, and capital R, it is the radius of ring, radius of the ring. Okay. Now we have to determine the moment of inertia of this ring about this axis. This is the axis which is perpendicular to the plane of the ring. Suppose this is the ring, then it is the axis of rotation about which the ring can perform the rotational motion. So, this axis of rotation, it is perpendicular to this, that is the circular, that is the uniform ring. That means mass is distributed along the circumference of this ring uniformly. Okay. So, capital M, that indicates the total mass, and capital R, that indicates the radius of the ring. Now, how we can determine the moment of inertia? For that purpose we have to consider the very small element of this ring. So, this is the very small element of this ring which is at distance capital R from this center IC, that indicates the moment of inertia of this ring about an axis passing through the center and perpendicular to the plane. So, this very small element, suppose it is having the mass, that is the dm. Now, we can determine the moment of inertia of this very small element dm, and then by integrating the equation we can determine the total moment of inertia of this ring, because this ring, it is made up from such small elements. So, first of all we can determine the moment of inertia for the small element having the mass, that is the dm. So, the moment of inertia of small element having the mass dm, that is di equals to dm into r square. So, this is the moment of inertia for this small element having the mass dm. Now, by using this relation we can determine the total moment of inertia of this ring about this axis. The axis, it is perpendicular to the plane. So, the moment of inertia of ring, first of all we are discussing about the axis passing through the center and perpendicular to, that is the plane. Okay. So, we have the relation for this very small element, moment of inertia of this very small element equals to dm, that is the mass of that element, into r square, which is the distance from the axis of rotation. Now, we can determine the total moment of inertia. So, the total moment of inertia of ring about an axis passing through the center, it is given by, on integrating this one. So, integration of di equals to integration of, that is dm into that is the r square. So integration of di, that gives the total moment of inertia of the ring. So you can write like this, that is the I. It is about the axis passing through the center. So we can write like this, that is IC equals to r, it is the radius and which is the constant one. So we can write like this, that is the r square, and integration of dm, that is nothing but the total mass. So in place of integration of dm, we can write like this capital M, and we have the relation, that is moment of inertia equals to m r square. So this is the relation for this ring. So moment of inertia of a ring about an axis passing through the center and perpendicular to the plane, it is given by IC equals to mr square. Now the second situation or the second case, we have to consider the axis which is passing through the tangent. So the axis passing through the tangent. So about the tangent, if the axis of rotation, it is passing through the tangent and again it is perpendicular to that is the plane. So for that purpose we have to consider again that ring. Suppose this is the ring, it is the thin and uniform ring. This is the axis of rotation which is passing through the center and perpendicular to the ring. So this is the center, and this IC, that indicates the moment of inertia about an axis passing through the center and perpendicular to the plane. Now we have to consider the tangent. Suppose this is the tangent, and the axis of rotation, it is passing through the tangent one. So suppose this is the point O, and the IO, it is the moment of inertia about this axis which is passing through the tangent, and the distance between these two axes, it is the capital R. Now we have to determine the moment of inertia of this ring about this axis. For this purpose we have to use the parallel axis theorem. So we can observe here these two axes are parallel to each other, and the distance between these two parallel axes, it is capital R, capital M, that indicates the total mass of the ring. Now by using the parallel axis theorem, parallel, that is the axis theorem, we can write like this, IO equals to IC plus M, that is the R square. Now we have the relation for, that is the IC, moment of inertia about an axis passing through the center and perpendicular to the plane. So IO equals to IC, that is nothing but the M R square plus, that is the M R square, and we get the relation IC equals to, that is 2 M R square. So this is the moment of inertia of a ring about an axis passing through the tangent and perpendicular to the plane. Now again we can determine the moment of inertia for this ring about any diameter. So for that purpose, that is about any diameter. So how we can determine the moment of inertia about any diameter? Now we have to consider the axis of rotation that is passing through the any diameter of the ring. So for that purpose again we have to consider a thin and uniform circular ring having the mass capital M and radius capital R. This is the axis of rotation which is passing through the center and perpendicular to the plane, and IC, that is the moment of inertia about this axis of rotation. Now we can consider any diameter for this uniform, thin and circular ring. Suppose this is the diameter, which is passing through the x axis, or this is the diameter which is passing through the y axis. Suppose we are going to consider these two axes x and y, and about from these two axes the axis of rotation is passing. If the axis of rotation it is passing through the x axis, then we can determine the moment of inertia of this ring, and that will be suppose Ix. If the axis of rotation it is passing through any diameter or from this y, then we can say that Iy, it is the moment of inertia for this diameter one. So Ix and Iy, it is the moment of inertia of this ring about the diameter which is passing through x and y axis respectively. So now for this construction we can use the perpendicular axis theorem. So by using, that is, perpendicular axis theorem, we can write like this, that is IC, so that represents the z axis, or we can write like this, suppose it is the z axis, then Iz, it is the moment of inertia, but it is equal to the IC because it is passing through the center of the disc and perpendicular to its plane. So according to the perpendicular axis theorem, Iz equals to, that is Ix plus, that is the Iy, this Iz it is equal to Ic, so you can write like this, Ic equals to Ix plus Iy. So this Ix plus Iy, that is the moment of inertia about the diameter one, but Ix and Iy are equal, because if we determine the moment of inertia about this diameter or about this diameter, then that is the equal one. So we can write like this, that is Ix plus Ix or Iy plus Iy, that is equal to the diameter, or we can write like this, that is Ix equals to Iy equals to I, that is the d, that indicates the diameter. So in this case we can write like this, Id plus, that is the Id, and Ic, we are having the relation for moment of inertia of ring about an axis passing through the center and perpendicular to the plane. So that is Ic, it is nothing but the mr square, and Id plus Id, that indicates the 2Id, and therefore the moment of inertia about any diameter, that is Id equals to, we have mr square by 2. So these are the relations for the moment of inertia of a ring about an axis passing through the center and perpendicular to the plane, that is Ic equals to mr square. If the axis of rotation it is passing through the tangent and perpendicular to the plane, then this is the moment of inertia, that is 2 mr square. If the axis of rotation it is passing through any diameter, it is passing through the x axis, that is Ix, it is the moment of inertia. If the axis of rotation it is passing through the y axis about the diameter, then Iy, it is the moment of inertia about that diameter. Then we have the relation, that is Id equals to mr square by, that is the 2. Again we have one relation for the moment of inertia. If the axis of rotation it is passing through the tangent, but now the tangent it is in the plane of the ring. Suppose this is the tangent, okay, but this tangent it is in the plane of the ring. Suppose this is the ring and this is the tangent. So this is the ring and this is the tangent. So you can say that this tangent it is in the plane of the ring, it is not the perpendicular one. In this case this tangent, this is the axis of rotation and this is the tangent, that means tangent it is perpendicular to the plane. But now we are going to consider the tangent it is in the plane of the figure, or we can say that it is in the plane of the ring. Suppose this is the axis. Now we have to determine the moment of inertia of this ring about this axis. Suppose IO, it is the moment of inertia of this ring about this, that is the axis which is passing through the tangent which is in the plane of the ring, and capital R, that is the distance between these two axes. Now in this case we have to use the parallel axis theorem, because Iy and IO, these are the two parallel axes, they are separated by the perpendicular distance of R. Now we can write like this, in this case by using the parallel axis theorem, that is parallel axis, that is the theorem, we can write like this, IO equals to, that is Iy plus, that is mr square. But Iy, it is the moment of inertia about any diameter, and we are having the relation for that, means we can write like this, that is Ix equals to Iy equals to Id, and we already determine the relation for moment of inertia of ring about any diameter. So we can write like this: IO equals to, in place of IY, we can put the value for ID, that is mr square by 2, because this is the moment of inertia about any diameter. So mr square by 2 plus, that is the mr square. Now IO equals to mr square by 2 plus mr square, that means it is 3 mr square by 2. This is the moment of inertia of a ring about an axis passing through the tangent, but it is in the plane of the ring. So these are the different cases for a thin uniform ring. We can determine moment of inertia about this axis, that is axis passing through the center and perpendicular to the ring. Then we get the relation IC equals to mr square. If the axis of rotation is passing through the tangent which is in the plane of the ring, which is perpendicular to the plane of the ring, then we have the relation, that is IO equals to 2mr square. If the axis of rotation is passing through any diameter, then we have the moment of inertia of that ring, ID equals to mr square by 2. And if the axis of rotation is passing through the tangent but it is in the plane of the ring, then you have the relation IO equals to 3mr square by 2. So these are the different cases for the moment of inertia of the thin and uniform ring.